Good morning to all of you. Okay, so I'll just start today's class, today's session, right? So the notes is, hope the notes is visible to you all, right? Last class I just started this moment area method. Okay, I also told you by this method it is possible to determine the slope as well as the deflection at any required point on the beam. Okay, at any point in the beam, we can be able to determine the deflection as well as the slope. It means angle of rotation of that point. Okay, so we can determine by this method. This method is best suitable for that, right? You may not develop a equation which gives the deflection profile of the entire curve. Okay, not necessary. Wherever required, then straight away you can determine the deflection as well as the slope. That is nothing but angle of rotation. Okay, so here I have drawn the. I will just repeat once again. Last class I told you, I am not sure whether how many of you have understood. That is why let me to just to discuss once again now. Okay, so that you will understand clearly. Here I have given the segment of a deflection curve, right? Deflection curve of a beam. The curvature is chosen positive. It means the curvature is downward. We are choosing it as positive, right? So here I am considering some segment AB of the deflection curve of AB, right? And also I have considered as elemental length here, right? Which is named as M1, M2, point M1, M2, which are ds apart along its length and dx apart in horizontal direction, right? I consider to point M1, M2, M2, which are dx apart in horizontal direction as well as ds apart along the curve, right? So this is called elemental length. From A to B is called segment of the deflection curve, right? So what we are doing, we do something. It's geometry, after all geometry. We want to get the deflection at any point, the angle of rotation, which are nothing but geometrical properties. Okay, geometrical quantities. Okay, we want to compute them. For that we do something, right? Geometrically we deal the profile, the deflection profile of the beam, right? So what we do, just have drawn tangent at A and point B. Okay, so two tangents have been drawn. The relative angle of rotation between these two tangents is called theta B. Actually, the angle made by this tangent at B with the tangent at A is theta BA. It is no relative angle of rotation of tangent at B with the tangent at A. Okay, this quantity is we are interested in it. This theta BA is nothing but the angle of rotation of point B minus the angle of rotation of point A. Okay, so the tangent at B makes theta B with the horizontal. The tangent at A makes theta A with the horizontal. Okay, so theta B minus theta A is nothing but the relative angle of rotation between these two tangents. Okay, theta B. Right, that is we are interested on that quantity. Other thing is the vertical offset. Okay, how I am defining some other quantity, that is vertical offset of point B from the tangent at A. This is the tangent at A. The vertical offset of point B from the tangent at A means from this B. I named this point as B dash from this point. This vertical offset I termed it as del B. Okay, some notation del B. Yes, right. So this is right. Apart from that, I come to this elemental length of the beam. Here I have drawn down tangent at M1 and M2. Okay. Here this vertical offset also I am defining. P1, P2, these points we are naming. And this vertical offset is say D del. Okay. Just. And also the angle, relative angle of rotation between these two tangents is named as d theta. How? Here, the angle subtended at the center of the curve is d theta here. If you draw normal to M1 and normal to M2, just the angle subtended at center is d theta. When the angle between these normals are d theta, the angle between the perpendiculars also d theta. Okay, that also d theta. I hope you all are hearing. No problem. It's okay. Right. So the angle between the perpendiculars also d theta. Okay. So this much information sufficient. Now below we have this M by A moment diagram. Actually, the beam will be having some moment diagram. Okay, that moment diagram is drawn, and the ordinate of each moment is divided by EA, which is called a M by EA diagram. Okay. Now, what happened? Right. Now, just I will tell you this offset. Okay. Actually, this vertical offset V del can be obtained. That's the same part. The first part I was discussing with you. Actually, this d theta is equal to minus m by a into dx. How? Already we have d theta by dx is equal to d square y by dx square is equal to minus m by a. This the first derivation we got, derivation term of a mean. In that we got this relationship, d theta by dx is equal to d square y by dx square is equal to minus m by a. Therefore, d theta is equal to minus m by a into dx. This relationship already we have. Now what we are doing, just we are integrating this d theta, okay, from for a segment a to b, okay. So integral a to b is equal to minus integral a to b m by a into dx. Okay. So here this integral a to b is nothing but angle of rotation at a upper limit where is 1 into angle of rotation at b minus angle of rotation at a. Okay, that is nothing but theta b is equal to minus integral a to b m by a into dx. This quantity as it is, which is nothing but this right part is RHS is nothing but right hand side is area of a by a diagram between A and B. Okay. So this equation may be stated as a theorem I told you in the last class. That is, which is called the first moment area theorem. First moment area theorem. The angle theta B is between the tangents of the direction curve at 2 points A and B is equal to the negative of the area of M by diagram between those points. Okay. That's what it says. What it means, the relative angle of rotation between these two tangents. The relative angle of rotation between the tangent at B and the tangent at A is equal to nothing but the area of the M by diagram between these 2 points. That's what the first moment area theorem states. Okay. Next, we are going for further. Up to this I discussed in last class. Just now I just briefly. Okay. Yes, last class I explained. We have gone through all this paragraph. We read each and every sentence in here, and we have just refreshing. Okay. So next I am going to the sign moment area. For that, what I am going to do, see here, we come here. Actually, in actual practice, this diffraction will be very minute, right? So the tangent at M1 and M2 will be almost horizontal, right? So that is why we can write, see here, suppose the elemental length M1, M2 is at a distance x1 from the point B, okay, at a distance x1, diagonal direction. Diagonal direction at a distance x1 from point B, okay. This elemental length, at a distance x1 and center. M1, M2 is the element. The center of the element is somewhere here. Okay. So its distance is x1 from point B, say. Now, what is this P1, P2 or D del, which is nothing but, it is assumption, we are making another assumption. Actually, the curve, the direction profile of the curve is almost flat. Okay. These two tangents are almost horizontal. That's why we can say a small assumption we can make this arc, okay, that what to say, this x1 into d theta is equal to this d del. D del is equal to d theta into x1 or x1 into d theta. Arc length, just arc length here. Okay, just arc length. Arc length means P1, P2. D del. So just this length into this d theta, that is radius into d theta, give you the arc length here. Okay, it's nothing but the vertical offset d del here. Okay, so that's what we have done. In a similar manner, this arc length del BA can be written, can be defined this way. Which way? Just let us see. Just we are coming to that, right? I will discuss. As the next step in the analysis, let us consider the vertical offset del BA between point B on the differential curve and point B dash on the tangent at E. Okay, good. Recalling that the angle of rotation theta A and theta B are very small quantities, and hence tangents at A and B are near the horizontal lines. That's what I told you. Okay. We observe from the figure that the vertical distance d del is nothing but equal to P1, P2 is x1 d theta, where x1 is the horizontal distance from the element M1, M2 to the point B. Since d theta is equal to minus m by a dx, we can write. Okay. So this is nothing but, okay, d del is equal to the vertical offset here. The vertical offset here, this d del, okay, P1, P2. This d del is equal to uh, uh, d theta into x1. Okay. But we know what is d theta. D theta is equal to minus m by a into dx. Okay. This already we have. What is that? I have written. Yeah. But that is equal to minus x1 into m by a into dx. What is d theta? Since d theta is equal to minus m by a into dx. How? Here. This equation already we got. No. D theta is equal to minus m by a into dx. The first derivation of differential term of a being. There we got this relationship. Okay. So in this, from this, d theta is equal to minus m by a into dx. Okay. That's what we are substituting here. Okay. So that is why the small vertical offset d del is equal to of the element element length of the beam minus x1 m by a into dx. This expression x1 m by a dx may be interpreted geometrically as the first moment of the shaded element area m by a into dx of the m by a diagram taken about the vertical line. Okay, vertical line through B. Right? It is nothing but the moment of area, this small shaded area. Okay, first moment of area of this shaded area about B. Okay, taken with respect to the vertical line at B means about not about B. Moment about B means what? Perpendicular distance only. No, you have to multiply the perpendicular distance. Vertical line drawn. The line passing through vertical line passing through B point. Okay, taking moment about B. That is the meaning of it, right? So moment of this small shaded area about B. That's what the RHS right hand side of that equation states, right? So that's what written here. So what is that? Yeah, that expression is over. Now integrating equation C between point A and B we get for the segmental length of the beam I want. That is equal to integral A to B d del is equal to minus integral A to B x1 m by A dx. Okay, equation D. The integral on the left is equal to del B. The integral on the integral d del means what? Del B, this one. Del B, here, this one. Del B, okay? Right. So del BA, that's what written here. The integral on the left is equal to del BA, which is the vertical offset of point B from the tangent at A. Please keep in mind, this is the vertical offset of point B from the tangent at A. Okay, right. The integral on the right represents the first moment with respect to point B. The integral on the right represents the first moment of area with respect to point B of the area of the MBA diagram between A and B. Okay, with respect to point B of the area of the MBA diagram between A and B. That's what it says. Okay, therefore del B is equal to minus integral A to B x1 m by A into dx. That is equal to minus first moment of area of the M by A diagram between A and B taken with respect to B. What is this RHS? This right hand side is nothing but first moment of area of the M by A diagram between A and B taken with respect to B. Okay, that's what right. That's what it says. Good. Just for reference purposes, I want to move this. Yeah. Right. Here. No. Yeah. So this equation represents the sine theorem. So we can state this equation this way. Sine theorem is the offset del BA, the offset del BA of the point B from the tangent at A is equal to the negative of the first moment of area of the MBA diagram between A and B taken with respect to B. Okay. So what it says, I will come to the figure and tell you the sine moment of area theorem. The sine moment area theorem I am telling you. The sine moment area theorem states that the vertical offset del BA of the tangent at B of the point B, sorry, of the point B on the diversion curve, okay, from the tangent at A, right, is equal to the first moment of area between the first moment of area of M by E diagram between point A and B taken with respect to B. Is it understandable to you? I told you just now I explained, right? Yeah, just now I explained. Is it understandable to you? Right? So just I'm recording your name for reference purpose, right? I will repeat. The Simon diagram states the vertical offset del BA, okay, of the point B on the diversion curve from the tangent at A is equal to the first moment of area of M by A diagram between point A and B taken with respect to B. Okay. If you understand, you can write it in your own sentences. You may not memorize or mark up the statement given here. If you understood this, whatever I discussed with you, you can write it down or you can tell in your own words. No need to memorize, right? That's what I want to tell you. Right. That is sign moment direct theorem. You will not memorize as it is in the textbook. It's a statement may differ from textbook to textbook. Okay, you can write in your own. Just I am telling you, see here, the first moment of area theorem is the vertical offset del BA of the point B on the diffraction curve. Okay, from the tangent at A is equal to the first moment of area of M by A diagram between A and B taken with respect to B. Finished. Okay, I finished the same moment of area theorem. Right. So I'm telling you my own sentences. I have not memorized these sentences as it is. Right? No problem. Now you got confused. I know very well. Every one of you got confused. What was our discuss all these things? It confuses us like anything. We say some vertical offset, tangent here and there. Why you have to do all such business? Obviously, most of you have got confused. Okay. Now I am going to apply it. Whatever I discussed with you, whatever so far I have discussed with you, referring to this figure, okay, you may, most of the majority of you may have not, might not have understood clearly, okay. So now you will be understanding. Now I am going to apply the theorem, okay, in order to determine the deflection as well as slope at any required point, right? Let us see. Now you will understand easily this theorem. So far, what we have discussed theoretically, the theorem, just I am going to apply. From the application, you will enjoy, you will realize how nice it is. Okay. For example, you take, I have a cantilever beam, right? Subject to point load at the free end, say capital P. I want to determine the deflection at the free end. Already you know how to do it by double integration method, right? We have a cantilever beam subject to point load at the free end P. Okay, B. The intensity of the load is capital P, right? The beam deflects like this. Say the angle of rotation here is theta b. You draw a tangent here. The angle made by this tangent with the horizontal is theta b, and the vertical this diversion at the free end is del b. Say, right? Now what I have done, I am drawing bending moment diagram. What is the bending moment diagram? What is the bending moment at the fixed end? P into L. The bending moment at the fixed end is PL. Okay. Moreover, only point load acting. That's why at the free end, the bending moment at the free end is 0. Okay, at the fixed end is TL, bending moment. So it is linear. That's why drawn like that. But I want M by EA diagram. PL is moment divided by EA. Okay, so it becomes M by EA diagram. So here the moment ordinate, I divided it by EA. Each ordinate is divided by EA here. Okay, the free end moment is 0. So now it has become M by EA diagram because simply I divided this M, whatever moment is here, by a term, the fluxual rigidity of the beam, EA I have divided here. That's why it is called M by EA diagram I have drawn. Now, as for definition, now what I wanted to determine the diversion at the free end node, I am applying the first moment of area theorem. First moment of area theorem I am applying. Just you take a point B on the diversion curve. Draw a tangent. Okay. Take that point A. You draw a tangent. If you draw a tangent at a point A, how it will be? It will be a horizontal line. Nothing but axis of the beam. Here. Okay. The horizontal line. If you draw tangent at a point A, it is nothing but a horizontal line. If you draw tangent at point B, it will be like this. Okay. Now, what is that one? Angle of rotation, the relative angle of tangent at B with the tangent at A. What is this is nothing but theta B. What is the relative angle of rotation? Because theta is horizontal. The tangent at A is horizontal. Please keep it in mind. The tangent at A is horizontal line. Tangent at B, this one. So I want theta BA. What is theta BA? Relative angle of rotation between these two tangents. Okay. So theta BA is nothing but theta B minus theta A is equal to minus area of M by A diagram between A and B. First one of area area of M by A diagram between A and B. That I have written here. Okay. Therefore, theta B minus what is theta A? What is the angular rotation at theta A? Which is 0. If you draw tangent at A, it is horizontal. So the angle made by tangent at A with horizontal is 0. Okay. If you draw tangent at A, it is horizontal line. So the angle made by that line with the horizontal at A, horizontal is 0. No. Because the tangent at A is horizontal. No angle of rotation. Angle of rotation at A is 0. That's why the relative angle of the tangent written here, theta B minus theta A. Okay, theta B I want to determine minus theta is 0. That is equal to area of M by diagram between A and B. I am applying the first moment of area theorem. So minus into this diagram. It's a negative bending moment. Okay, we are solving bending moment. That's why negative. So that's why the moment itself negative. No, that's why minus area of this triangle off into PL by EA into this L, which is nothing but area of M by A diagram between A and B. Okay, so I have written here, which is PL square by 2A. You got it. You got the angle of rotation at B. Already we derived by W method the angle of rotation at B. Now so you got the same expression PL square by 2A. There I used the notation W, capital W instead of P. Please recall. Instead of P, I have used the capital W in my previous discussion, W derivation method. There capital W and square by 2A, I am using to represent point of capital P. So PL square by 2A. Same expression we have got by applying first moment area theorem to this beam. Okay. Next I am going to get the definition here, del B. Okay. The horizontal. Okay, something I written. Del B. Del B is equal to the vertical offset. The vertical offset of point B from the tangent at A. What is the tangent at A? It is horizontal line. The vertical offset of point B from the tangent at A is this one. This del B. This del B. Okay. So, 1 minute. Just for suppose I want to just carve like this. Right. Yeah, that's what. Del B. So, the del B is equal to the vertical offset is nothing but direction at the point B. Del B equal to minus moment of the area of M by diagram between A and B taken with respect to B. Okay, I have written here. That is equal to minus of minus. Now the moment diagram is with negative sign because it's argumenting moment. Minus half into what is the area here? PL by EI into L. Okay, because the triangle, that's why half into height into length. Okay, of BH of BH I have written here, right? Into moment. First moment of area with respect to which point? With respect to B. B is here. What is the central distance from B here? 2/3 L. From here, from the base, it is 1/3 L. From the vertex, it is 2/3 L. The centroid is located. No, that is why 2 by 3 into L. Moment. First moment of area of this M by A diagram above B we have to take. So that is equal to PLB by 3A. You got this same expression we obtained when we have done it by double integration method. Here we have applied the principle of first moment of area theorem. First moment of area theorem I have applied. Okay, the vertical offset here is nothing but del B. How the tangent at B. Okay, sorry, the point B, the point of B on the diffraction curve. The vertical offset of point B on the diffraction curve from the tangent at A. The tangent at A is horizontal. That is why the vertical offset is here is nothing but del B. So the vertical offset of the point B on the diffraction curve from the tangent at A, del B is equal to minus first moment of area of M by diagram between A and B taken with respect to B. So we have got it PLB by 3A. So from this discussion, you have understood very clearly how this theorem, first moment of area theorem, Sine moment area theorem. By applying them, how we determine the angular rotation as well as deflection at the desired point, at the required point of on a beam. Okay, so this is a very simple example. From this example, you clearly understood the theorem, how to apply the so far what I have discussed here. Okay, this theorem, how to apply it. Right? We will proceed further. We will discuss further. Next, suppose you get a numerical problem. Just here with notations I am explaining. If you get with what is that? Just reference purpose, I am keeping your name like this. Okay, recording purpose. Right. So see here, you have a beam, cantilever beam like this, subject to UDL, nearer to the free end. Okay, nearer to the free end, it is spread over length of L by 2. Okay, our intensity small w. If you get the numerical values, how to get it? Okay, how to deal it? Just with the notation I will explain, right? So I'm interested in determining the deflection as well as angular rotation at the free end. This is the deflection profile of the beam say. The angular rotation at the free end is theta b. The deflection is del b, right? Now we have drawn the M by A diagram. This moment diagram we can draw because if any beam is given like this, you know how to draw bending moment diagram. Already you have studied on the title bending moment shear force. Your basics of mechanics of solids you have studied. You know how to draw a moment diagram. You draw a moment diagram and divide each ordinate by EI. So this is the 3 by 8 WL square. This is WL square by 8. You can compute. You do it. Later you do it. You know how to draw. You must be thorough. Already you are very thorough. How to draw bending moment diagram for any beam given like this. Okay, draw this beam. You divide each ordinate by EI. Okay, so this is called M by A diagram. You draw an M by A diagram now. Okay, so for simplification, what we do, we divide this M by A diagram into standard plane figures. Okay, this I have divided into a rectangle, here a triangle. This is called a parabolic spandrel. If it is like this, it is called spandrel. Okay, parabolic spandrel. Like that, we have divided into standard plane figure. This area for simplification. Okay, now the del B, I wanted to determine the angular rotation at free end. Del B, okay, is equal to del B minus del E, right? Del B is nothing but relative angular rotation between the tangent at A B and the tangent at A is equal to del B, angular rotation of tangent at A B minus angular rotation of tangent at A. Okay, del B minus del E. Therefore, del E is 0 because if you draw tangent at A, if you draw tangent at E, it is horizontal. That's why no angular rotation for the tangent at E. That is why del E is 0. So del B is equal to the angular rotation at B alone is equal to minus area of the M by diagram between A and B. That is equal to minus area of M by diagram between A and B means this area okay, A1 plus A2 A3. This area, this area, this area. A1 is equal to it's a spandrel. That's why it is 1/3 into BH. Okay. So 1/3 into here it is L by 2, no. That is why L by 2 into WL square by 80A BH. This is B, this is H, this is B for this spandrel. Okay. So I minus 1/3 of this one. We got this area. Next A2. Where is this rectangle? This is equal to what is this? WL square by 80A into this length, which is L by 2 here. Okay. So we obtained some expression for that. A3 is equal to this triangle. Half into L by 2 into this one. Which one? This ordinate. Only this ordinate. This ordinate is what? This minus this. 3WL square divided by 80A minus WL square by 80A. That is this ordinate. Okay. That is determined as 2WL square by 80A. 2 by 8 WL square divided by EA. Okay. This minus this if you do it. This ordinate. Okay. Only this ordinate. Right? We have done it. We got some expression. Now, theta V equal to minus of all these things, sum of. So you'll be getting some expression. 7WL square by 40 dA. We got it. So we are not interested in just I'm telling how to determine angular rotation at the free end if you get any problem like this. If the numerical values are given, you have to compute this way. With the notation, just it has been shown. Okay. This is just an example with the notations. Okay. Without numerical values, just with the notations, you are getting a expression like this. Okay. Suppose if you want to determine the deflection at the free end, right? If you want to determine the deflection at the free end, del B is equal to minus first moment of area MI diagram between A and B taken with respect to B. Okay, already we know sign moment of area theorem. Del B is equal to why del B? How del B it is? How it is the deflection at B? It is the vertical offset of point B on the deflection curve from the tangent at A. From the tangent at A is horizontal. Vertical offset of point on the deflection curve. This is the point B on the deflection curve. Okay. Vertical offset is this one. From tangent at A. This is the tangent at A. This is the vertical offset. This is nothing but the deflection at the free end of the beam, del B. So therefore, del B is equal to minus of first moment of area of M by diagram between A and B taken with respect to B. So with the notations available, we have taken moment. In this, you have to be very careful. The central distance of each one. I will explain. It may get bored, but no problem. I will explain. See here. This is first area. This is first area. W cube by 48 EA. Which one? Here we got minus WL cube by 48 EA. A1. A1 we got area. This is A1. Okay. From here, moment no, it's standard distance. This standard distance is at a distance, what distance? At a 3/4. From here it is 3/4, from there it is 1/4. See here, if you take a spandrel, like this, the standard distance is 3/4 from here and 1/4 from here. Please keep it in mind. It's not a triangle. It is a spandrel, parabolic spandrel. Okay, that is why from here the standard distance is 3/4. From here, the standard distance is 1/4. That's why it is multiplied. The first area, moment of the first area, about point B is written here. Next minus the moment of the signed area. Signed area we have determined here. Minus WLQ by 16A. Okay, so minus WLQ by 16A into this one, no? Which one is the signed area? This is the signed area. Okay, so from here, moment is taken here. That's why from here, it is L by 2 plus L by 2 divided by 2, that is L by 4. L by 2 plus L by 4 from here, the distance is. Okay, that is why that is given like that. L by 2 plus, okay, then that it is written 3/4 here. Other one is same. L by 2 plus L by 4, which is nothing but 3/4 here. I have written. Okay, next third area, minus WLQ by 16A. Minus WLQ by 16A into from here. This is the third area. From here, it is L by 2. L by 2 plus, this is triangle. Triangle is here. From here it is 2/3. From here it is 1/3. Okay. So 1/3 L by 2. Right? 1/3 L by 2. L plus 2, L by 2 plus 2/3 L by 2. It is wrong written here. L. 2/3 L by 2. It's supposed to be. Okay. So 2/3 L by 2. Here it is wrong written, I think. 2/3 L by 2. Right. From here it is 2/3. Is L by 2 only? No. From here it is 2/3 L by 2. From here it is 1/3. Right. So that's all. Everybody is waiting. I don't know. Many student latecomers came and was waiting. I have to check up. Right? So no problem. Right. So please don't get confused. With some notation I am explaining. I just now explained with some notations. Okay. So it is simply something. We will see it in the next class because by this time you might have got confused. Because I dealt with the notation and all. For me it looks easy. Because you are a beginner. How you understand, I don't know. I am explaining. I am thinking that I am explaining clearly. But since most of you are, majority of you are below average students, I don't know. Average and below average only we have nowadays in our classroom. So don't mistake me. I am telling the fact. Right? So you may feel it hard to follow and understand says something, what he says. Please kindly, you should not expect because you are doing engineering course. It's not a easy going course. It's a very tough course. Okay. Most of you have sufficient knowledge. The only thing is lagging is hard work. People are not prefer. People don't prefer to do hard work because of they are living in the electronic era. there's a distraction. You are spending most of the time with your cell phone and TV. Okay, obviously you don't find time to sit and study textbooks. So that is, you must have some self-control. Otherwise, it's very difficult to grow, right? If you don't have self-control and determination and maturity, it is very difficult for you people to grow. That's what I would say. You have to limit your entertainment, your recreation, cell phone and all. You enjoy life, no doubt about it. You are living in a wonderful era. Excel powerful tool you have with you in your hand. But use it in a matured manner for knowledge improvement manner or improving the maturity manner. Just to use them, right? So with this, I will stop today because next class I want to start this series about game. By this time, most of you got confused. I know many of you may not be clear. Please kindly go through this. I am telling you, I will send the notes. I will send the notes. So far, I have not sent. But definitely, I will send it today. Don't worry. Definitely, I will send it to you today. Just for attendance purpose, just I want to record your name once again. Just wait for a few minutes. I will record your names. Okay. Your names have been recorded for attendance purpose. It is well recorded, right? So 2 minutes you wait. Nearly 52 of you are attending the class. Okay. All your name, Abdul Vidya. Okay. All your name have been well recorded, right? So 3 minutes now. Just you are, I'm not sure how many of you are keenly listening the class. That I'm not sure. Whether you simply switch on and go somewhere and you are attending, whether you are listening to the lecture and whether my voice is pleasant to you or and all, I'm not sure about it. Okay, you have to learn. That is the way to go. Do not get bored or you should not get irritated. You have to listen to others and try apply your mind and try to learn somehow, right? So and moreover, every time I'm giving notes, but I'm not sending it. Last I told you, I'll send the notes. Definitely by today I will read it. Okay, you can read it because without notes, how do you read? I will send it. Most of the books, whatever I discussed, it is available. However, I will send the notes. Okay, so that you can refer it. Just I will stop recording. We will discuss, right? So I will stop recording.